TensorFlow. I'm going to walk through another tutorial today. Yesterday I installed and worked through the very basic tutorial, just kind of set it up and get familiar with the software. Today we're going to go through the next tutorial and see if I feel any more familiar with it. Thanks for everyone who left comments about whether you didn't like having the installation part of it or you did, and to those that tipped in and said, hey, you can just skip. That's really helpful for people. I'm really glad you guys did that. So let's jump right into this here. And of course, we're at the bottom of our tutorial here, and we're going to go to the next tutorial. We'll just click that link. This takes us back to the main page. Not really where I wanted to go, but that's all right. Go to tutorials, deep MNIST for experts. Clearly, you finished one tutorial, you are now an expert. No problem at all. All right, so let's go into that. See where we're going. Jump right into it. I'll flip back here. You can see I've already got my Python open. I've got my old data file. I copied it over to a new file, tutorial2.2. I plan to just wipe it out. Right now, I'm not putting these things in a Git repo or anything because this is just me playing around, seeing what I like. If I was doing some data science of my own, trying to analyze some data set, I probably would. But here, I'm choosing not to do that. I don't think this is a serious enough need right now. But if it gets to be serious, I'll probably do that. All right, so what are we doing here? Yes, TensorFlow is a powerful library for large-scale numerical computation. Introduction for beginners. We don't need to do that. We already did that. First load up the MNIST dataset. This is what we did before. Load the MNIST dataset. I believe we have exactly this. MNIST data one hot true. Yep. Oh, they don't have the slash in here anymore. That's interesting. I wonder if that's going to make a difference. Well, let's find out. And by let's find out, I guess I mean let's not find out. Let's just take that out. So let's load in some TensorFlow using Slimux. It's great. Highly recommend it if you're doing data analysis. Did that work? Hang on. There we go. Okay. Just a couple momentary problem there, but no problem. All right. So we need to read in the data. This MNIST, it's the same data as last time. We're just going to be building a different model of it. So for those of you who are just joining us, that's the Postal Service 28 by 28 pixel images of digits. And so the goal is to build a model using those to be able to recognize with a machine what digit some picture is, so that a human doesn't have to look at it. Save yourself a lot of trouble. All right, so we have the data. TensorFlow relies heavily on C++. A lot of this stuff is going to be what we saw before, pretty much, since it's the same. This is just the advanced tutorial. We're going to use convenience of interactive session class. Makes TensorFlow more flexible in how you structure your code. I like the sound of this. This might answer some of the issues that I had before. Did we use this last time? I don't think we did. Interactive session, let's search. We didn't. Okay, so this is good. This might answer some of the concerns that I had previously, not being able to see inside what's going on. Allows you to interleave operations which build a computation graph with ones that run the graph. We'll see exactly what they mean by that later. Particularly convenient when you're working in interactive contexts with like IPython. Hey, what do you know? That's exactly what I'm doing. Thanks, Google. If you are not using an interactive session, then you build the entire graph before you starting the session and launching the graph. Okay, so yes, this is exactly what I want. Let me copy that. Copy that. Interactive session. And I want to do one thing, set it on paste mode, so if I'm pasting several lines, Vim will not automatically indent them. Normally you want automatic indenting in Vim, it's very smart and helpful, but if you're pasting a whole bunch of lines of code from something, that's just going to ruin everything. You don't want that. You'll have the worst day. Okay, so we're going to have an interactive session this time, so hopefully we can build the graph and then run part of the graph and poke around and see what we get out. And that's what it's all about, being able to poke around with the data. All right, computation. Do official American in Python. Yes, we're going to use other libraries, not things in Python. Things like NumPy. Yeah. There's going to be a lot of overhead switching back to Python every operation. Oh, yeah. So I guess that's the downside of the interactive. Computation GPUs, high cost of transferring data. Data transfer is often a bottleneck. You got to be concerned about that. 1 second here. Yeah, whatever. This is good. All right. Actually, let me pause just for a moment here. Okay. Sorry about that. Wasn't sure if my sound was working. Oh no, what have I done? Okay. We should be back now. Sorry again. We're going to build, what are we doing here? TensorFlow does the heavy lifting outside Python, of course. It's all C++, compiled code in the background. This approach is similar to using Theano or Torch. So Theano is probably something I'm going to look at later. Again, I was planning to look at that yesterday before learning that TensorFlow came out. Torch, another similar kind of tool set. So maybe we'll get to those in the future. The role of Python code is therefore to build the computation graph, tell how things are supposed to look together. All right, so that's all kind of familiar stuff. We're going to use Python to describe whatever this graph of computation is, and then it will, Python's sort of the arbiter, it will tell various libraries, hey, do this, hey, do that, here's the data. We're going to build another softmax regression model, which I believe is the same type that we built last time. So a single linear layer, so it's very similar to linear regression, but for categorical data again. If you were with me yesterday, that's the, if you choose to take a bus to work, a train to work, or drive your car, there's a category. And there's no inherent order to the categories. This is another key point. It's, with digits, nominally you can consider they're in order, but for the purposes of writing them, that doesn't really matter. But that would imply a different kind of model, but we don't have that here. All right, placeholders. So we got to have our placeholder variables. These, if I recall correctly, are going to be our input. The x's are definitely input. They're placeholders, a value that will input when we ask TensorFlow to run a computation. Yes. So this is going to be stuff we're going to send to the graph to run. So I believe we should already have this. X equals tf.placeholder. Float, none, 784. Yep. So it's 784 long, which is 28 squared, of course. That's one image. And there's no telling how long it's going to be. And this is the y bar, which that's the class of the digits. So it's the probability of that digit, I believe. X is, here's just what I just said repeated. It also consists of a 2D tensor. Each row is a one hot. Oh, sorry. That's for a given image that we've marked, which digit is it. So if the first position is marked, it's a 0. If the next position is a 1, it's a 1. And they've done it in this one hot fashion. So there's only ever a single 1 in that 10 long array, and the rest are zeros. You can check yesterday's video if you want to see more of that, or just look at their tutorial. It's probably quicker to find and search. All right, the shape argument to placeholder is optional, but allows TensorFlow to automatically catch bugs stemming from inconsistent tensor shapes. That's probably helpful. And it's just helpful for you as the user, if you're defining this placeholder, to say, oh, right, this is supposed to be this. That'll help you remember. That's just generally a good thing to do. All right, so again, placeholders are kind of these input variables, it looks like. Or the input things we're going to put into the graph. Variables are things that we're going to compute inside the graph. So there's this weight W. These are sort of coefficients that go along with each pixel, or you can think of it as coefficients going along with each pixel. That's sort of a simplified view. If you only had, say, one pixel and you were doing simple linear regression, y equals bx, y equals mx, this is sort of your m. In fact, you just flip it upside down, m and w, same thing. Whatever. But that's the kind of thing you're going to estimate. B is the inherent bias. Some digits are simply more common than others, regardless of anything else. The bias will help capture that, so that our our model will be similarly biased. So yes, a variable is a value that lives in the computation graph, can be used and even modified by the computation. One generally has the model parameters be variables in the machine learning context. Sure, that sounds fine. We pass the initial value for each parameter in the call to tf.variable. Yes, we initialize it to zeros, so you could initialize it to whatever if that matters for your graph. That's not a big deal. I think they even say that it doesn't matter what you want it to be. But probably it's good to make them something that you know what it is so that you can get very predictable results. In fact, here we're going to initialize our variables in the session.run. tf.initialize all variables, which you recall from the old. Hang on. Now I gotta. Oh, there we go. Oh, I'm still in insert mode. I might have destroyed it. Hang on. Alright, benefit to tmux. If you somehow screw up a pane, you just destroy it. Kill pane 1 down here in the lower left. Yes. Okay. And we'll make a new one. And I'll once again open top 2. Hang on, let me remove the swap file. There we go. Quick recovery, no problem. And by quick recovery, I lost everything. Alright. Not a problem. We can run back up here. Grab. We just needed this. This is the only thing now. I am opting not to switch it to paste now. Most of this looks like single line stuff. Alright, I got my X's. We got this cross entropy business. That was there, that was there. That's all old way. Okay. We got our data. We got that. Got our X and our Y bar. Got our W's, got our B's. We're going to run just this little part. Alright, I got to make sure I run this stuff, of course. Maybe that was a problem. Session, it's a new Slimux, so it says yes. I'm running the CPU version because I couldn't get the CUDA version to install right. It couldn't find my CUDA library. I don't know if that's something about Arch Linux installs it to a strange place or what, but that's okay. It doesn't really matter. Okay, so we just ran that little bit. What can I look at in session? That's what I'm curious. What was the graph? Graph that was launched in this. Yeah, thanks. Okay. I'm just curious. I wonder if I can like generate a dot of the graph so I can actually view it very cool. Or like an ASCII art one. That would be even better. Oh, you can look at the seed. I guess there's no seed. No doc string. Okay. Yeah, figures. Okay. I often like to poke around inside the graph, or inside the whatever Python things I'm looking at, just to see what's there. All right, so we initialize the variables. We did that before. We're doing it more. We're doing it again today. All right. Predicted class and cost function. All right, so this is the actual regression model. Again, we saw this all yesterday. Yes, it's as simple, this softmax things, this multinomial logit model for modeling categorical data. Again, it reduces to the simple function of essentially wx plus b. So, which is that same as just a line, mx plus b. Same exact kind of thing. The thing we're trying to minimize is called the cross entropy, which is sort of a measure of how much information is in something. This is slightly different. This is the y bar versus y. Again, it's all the same stuff as yesterday, so we're going to see what the expert part of this is in a little bit. But I guess all I have to do is move the old way stuff. No problem. Alright, what do we got? Now we're going to train the model. Okay. Again, this is the same as before. This is our learning rate. How quickly we're willing to change the variables inside the machine learning model. So if you want to learn faster, you want it to scale faster, you might increase the learning rate, but that's comes at a risk that you might overtrain more quickly as well. And of course, what are we minimizing on? Cross entropy. Cross entropy here is this, think of this more as an expression or an equation, not that we have computed the cross entropy just now. So we're building the graph. So I believe this is the same as yesterday. In fact, it exactly is. So I can just move that down. I'm probably not going to need this anymore because I already initialized the variables. All right, what do we got? So TensorFlow actually did is did in that single line is add new operations to the computation graph. Yeah. Although I don't see how that gets added to a particular graph as yet. Although I guess it's building up pieces from cross entropy and other stuff. Alright, well that's cool. These operations included ones in the compute gradients, compute parameter update steps, yada yada yada. Returned operation train step when run. So when you run train step with the appropriate data, it will actually train the model. And that's what these lines do here. So it looks like I don't have to, I no longer have to do this sesh stuff because I'm doing train step.run is built into it. Why is that? I just did sesh.run here. Interesting, okay. Now, is that the same? That is only batches of 50. Interesting. Alright, well, it's on game. Batch X's, batch Y's, batch 0. Hang on. Batch 1. I don't know why these use a slightly different styling than the yesterday's. Yesterday they had XY equals this, which makes perfect sense. It's a good Pythonic thing to do. Here they just make it a batch and it's batch 0, batch 1. Did they get to this later? Do they use other things in batch? Maybe. 1 to 15. Batch vectors. Doesn't really look like it. Still a couple more. Let me see. No. Okay, they don't. So I'm gonna not change that. Deviate from the tutorial. We're gonna find out what happens here. Okay, so I've got this right here. I guess I don't need that. I don't know. Maybe I will. Let's go 5 lines. Put that right there. No problem. Should probably run some of this stuff, shouldn't I? Last thing I did was run this session, I believe. Let's get that. Let's get that. Get that. And this. And I'm going to tell my IPython to not auto-indent anymore. Normally, like, auto-indenting in IPython is great. But when you use SlimeUp, you could just use an actual text editor. You don't have to try to edit your program in IPython. So even though if you set up your readline library right, you can have most of the same things, I like having a proper text editor to do all my work in. Even if it's just for simple quote-unquote data analysis of not writing an application. Alright, so there's that. I did a whole bunch of sesh.run, applying train step with my data. Alright, what are they saying? We'll have 50 training samples, run train step. Yes, we input our X's. Our X's, those are the images themselves. The Y's, those are the categories. And so we're pulling these out of the training data set. You can replace any tensor in your computation using feeddict. It's not restricted to just placeholders. Interesting. So the placeholder is just a specifically designed for that, maybe. Okay, so how'd the model do again? Correct prediction. I think I have that already too. Yeah, I think we do. Let's go ahead and pull this up. Did my session end the same? Oh, train step to run. Oh no, I did this wrong. Oh no. It might not have mattered. It probably. Yeah, okay. So train step. How does train step have a built-in session? That's what I want to know. Alright, you know what? Just to be paranoid, kill this and start a new one. I want to know how that happened. I want to auto-indent again, because that's what I do. Alright, so right there we make the session. That's good. Let's define our model, softmax business, what we're going to optimize on. This is how we train. So now I'm doing, but how does train step know anything about the session? Is it just default to that? What if I wanted multiple sessions? Like, that looks like it did something. That's what I'm curious about here. Is there something really obvious I'm missing? Somebody shout if I am. Session is this. I initialize the variables. Maybe that's how it knows? Because I'm screwing with these variables? Maybe? That's the only connection I can see right now. Like before, yesterday, in the basic tutorial, it was sesh.run. You put in the train step, and then you put in whatever this function is, and then your data. But here I'm just saying I have the function and run it. And it assumes, because these variables are attached to a particular... Are they even attached? Oh yeah, they are attached, because they're attached here. And they're used here and here. Okay. Maybe that's how it does it. That's not the super most obvious thing to me. All right, TF argmax 1, TF argmax y versus y bar, yada yada yada. Boom. I believe y bar was our. Those are actual predictions. No. Y bar is the real numbers. That's right. Because they get put in here. So y must be our predictions. Right, and that gives us the vector of true, false, false, whether they equaled or not. So let's find out how that goes. We just trained. Boom, boom. What's our accuracy? Right, haven't run it yet. Of course. Accuracy.eval. Aha! That's the magic I want. And this Python 2-ness here that we can work around, I'm sure. And actually, I just want a equals. Do that. And then I want to look at a. All right, so yeah, about 91%, a little less. That's okay. We can live with that. Let me know if it's getting too dark in here. It is kind of raining and cloudy outside. And I haven't actually turned the light on, but it seemed fine. Okay. So, yes, we have the expected accuracy. Getting 900% at MNIST is bad. It's almost embarrassingly bad. But thankfully, we can fix it. Aha, so we'll be getting into something new now. Shifting from this very simple multinomial logit into something moderately. Here's a slight typo. Pointed out to Google. Sophisticated, a small convolutional neural network. So this is what people really dig. People love neural networks these days. But I want to caution that getting 91%, you just spent 5 seconds doing this, and you got a very good you got what is actually not that bad accuracy on this particular data set. Yes, lots of people have done much better. A lot of data sets, 91% may be the best you're ever going to get. So it's important to judge, does this problem need a neural network to solve? Maybe it does, maybe it doesn't. For statistical, called generalized linear models, which I believe softmax is one of, you can get information on how each variable, in this case like how each pixel is impacting the final result. Depending on what you're trying to model, that can be really useful. Like I studied transportation statistics, so knowing how wide the road was, it was important to know how that specific variable impacted the problem. Or impacted your result on, say, like the road safety or something. Because you want to be able to control the road safety, really. Here you're trying to model, you're trying to guess what is the category of something. But in other situations, you might be trying to control that. So you want to know, well, how do these variables actually interact? So, right tool for the right job is the short of it. But in this case, we just want to know as accurately as possible what is this digit. So let's get to something a little more advanced, shall we? Weight initialization. We're going to create a lot of weights and biases. So before we sort of had this one big vector of weights, now we're going to have many. Once you initialize the weights with a small amount of noise for symmetry breaking, prevent zero gradients. That makes sense. That's common. We're using ReLU neurons. So I'm not sure if this is different from a perceptron. You know what? Well, let me look it up. That's the easiest thing to do here, right? Don't know? Search Google for ReLU neurons. Rectifier neural networks. Wikipedia, the font of all knowledge. Tell me. Rectifier has an activation function defined as f of max 0 and x for access to input neuron. This is the ramp function. Okay, so it's a little different from a linear one. It's a little more interesting. That's okay. Leaky RUs, noisy RUs. Oh, I could spend all kinds of time reading this. Cool. It's a good practice to initialize them with a slightly positive initial bias to avoid dead neurons. That is, if your neuron shifts to sort of all zeros as its weights, it doesn't matter what goes into it, it zeroes it out, and it's not passing on anything to the next layer. So it's, as they're saying, effectively dead. It's not part of your computation any longer. So that's why they say slightly positive initial bias. So you have something going there. It is possible, however, that you could find maybe you don't need all those neurons. If they're not helping, maybe they're just, they could be overtraining your model. So it's important to use the right number of variables. I haven't seen in here, but in other contexts, I've seen to score like the Aka-Ike information criterion. So you sort of penalize your score and how good this model is based on how many variables you're using to model it. That's one way to do it anyway. But let's get back to this. So we're going to make some functions here. What are we doing? Instead of doing this repeatedly while I build a model, let's create two handy functions. So we're going to weight a variable, given a shape, TF that truncated normal, so from a certain distribution, make something of this shape with this standard deviation. That makes sense. And then we return the TensorFlow variable of the appropriate distribution. Then we're going to bias a variable. So we're going to start with a constant of 0.1, I guess. And we'll learn what those are. Of the desired shape, and we'll return a variable like that. So this one we're pulling from a distribution. This one is just a positive constant in this shape. So like an array of that shape. So I suspect we're going to initialize using this, and then we'll muck with them a little bit using this. We'll find out. For now, we can just copy these. I don't actually have to copy that. Sometimes I just do it anyway. You can yell at me for that. All right. I'm gonna set paste now because I'm actually pasting stuff. I want to remind myself what this is for. God, why don't they? I strongly prefer 4 spaces to my indents in Python rather than 2. So that's a little annoying that they do that, but that's just a personal preference. Yes, initialize variable with noise. Initialize variable with small positive bias. And let's make a better model. Cool. All right, convolution and pooling. TensorFlow gives us a lot of flexibility in convolution and pooling operations. How do we handle boundaries? What is our stride size? All this fun stuff. I'm going to choose the vanilla version. I do hope they explain exactly what that means. Convolutions use a stride of 1 and are 0 padded, so the output is the same size as the input. Our pooling is plain old max pooling over 2 blocks. All right, I want to see what they mean exactly when they say convolution uses a stride of 1. Architectures, convolution, and pooling layers. Oh, CSA, convolutional neural networks. Hey, what do you know? So part of this is to show that when you're not sure what exactly someone's doing, it's just fine, stop, pause, spend a few seconds for trying to learn, like, all right, what is this thing they're actually talking about? Very similar to ordinary neural networks. They're made up of neurons. Each neuron receives inputs, yada, yada, yada. They still have a loss function. Support vector machine or softmax. Okay. on the last fully connected layer, yada, yada, yada. So what's changed? Make the explicit assumptions that inputs are images, which allows us, I see. Allows us to encode, so there's a certain, use a stride of 1 or 0 padded, so the output is the same size as the input. I would have thought that meant certain properties into the architecture. Makes a forward function more efficient. So if you assume the inputs are images, I would have thought that means they imply this is a two-dimensional array, and you know that there's 10 columns or whatever, so that the first element and the 10th element are in fact right next to each other, just one is on top of the other, and you can use that extra information. But is that what's going on here? Hidden layer 1. Oh, they put our neurons in dimensions. Is that the case? It's visualized in 1 of 3 layers. Interesting. Transforms the 3D input to a 3D output volume of neuron activations. Interesting. As opposed to just a simple layer. ReLU input layer. Compute the output of neurons that go to logical regions. ReLU, this is what we're using. The activation. Pool performs downsampling. So you shrink down whatever you had at compression. Alright, so you start with input. Looks like you upscale a little bit. Get to a bunch of typical nodes. Okay, so we're using multi-dimensional layers is the catch here. Alright, so what are they doing here? Convolution is a stride of 1 or 0 padded, so the output is the same size as the input. I think that's the key. Pooling is a plain old max pooling over 2 by 2 blocks. Keep our code cleaner. Let's abstract those into functions. Sure. Let's do that. Convolutional 2D. Bam. Again, just for my own sanity. Oh gosh, that's terrible the way this font scaled here. That's an M, but it's just like a square with the corner chopped off. It's a floppy disk. For those of you that remember the old floppies. Don't copy that floppy. All right. First convolutional layer. So now we're going to implement the first layer of whatever we're doing. Convolution followed by max pooling. Convolution will compute 32 features for each 5 by 5 patch. Right, so that's it's an image aspect of it. Its weight tensor will have a shape of 5 by 5 by 32. And 5 by 5 is really only 25 things, but that's okay. First 2 dimensions are patch size, the next is number of input channels. So is that the red, green, or we don't have red, green, or blue here, right. So there's only one, which is how dark it is. This is a black and white image. Or this is a grayscale image. Last is number of output channels. Right, so the number of features we're going to get. So we're sort of putting in 25 things in a particular shape, so you can combine those things in interesting ways, and that's how you can end up with 32 features coming out. All right. We also have a bias vector for component. Right. We will also have a bias vector with a component for each output channel. Right, so just is this image generally light or generally dark? I believe, or not this image, this 5 by 5 patch. So this is very similar to before, just now this is on a small section. Wow. Hang on. Copy that again. Seem to have lost my copy mojo there. There we go. Okay, much better. Let's run some of this stuff so I don't forget about it. This is a problem when doing tutorials, is often forgetting to run things. Activate all those. That one. Okay. So we define some convenience variables that'll help us initialize variables. We're using those right here. And we're preparing to get our variables for making the layers pretty easy. 1, 2, 2, 1. Okay, I'll have to take a closer look at that, what that exactly means. To apply the layer, we reshape X to a 4-dimensional tensor. That's right, we're moving beyond the 3rd dimension. With the 2nd and 3rd dimensions corresponding to image width and height, and the final dimension corresponding to the number of colored channels. Again, this is just brightness is our only color channel, so there's only one. It's 28 by 28 image. What is this -1 about? Oh, you start backwards? Is that how reshape works? Let's find out. Let me copy it over here first. Whoop. Lucked out on that one. First letter was an I. Alright. tf.reshape. Does this work like I think it does? Reshapes the tensor. Given a temperature, the shape is a special value, -1. The tensor is flattened, and the operation outputs a 1D tensor with all elements in tensor. That's really useful. That is good to know. That's flattening an array is something that, like, I often have to hack together a solution for. So it's good to see that they have a quote-unquote real solution here that just makes it dead simple. Alright, so you flatten it out. It flattens out the input. Shape is special -1. Tensor is flattened, and the operation outputs a 1D tensor with all elements of tensor. Shape is 1D or higher. Let me just see an example, see if I can reshape, yada yada yada. Alright, well that's all it is, too bad. That's something where it'd be really good to just take a given input variable and be able to play with it and see, oh, what does this do? What does that do? I don't believe that is a possibility here, though. Because image is just, yes. Image is just this tensor thing in the middle of this computational graph. Alright, then we convolve x bar image, oh, x underscore image. Did I? Oh, whoops. So I get, there we go, much better. We convolve x image with the weight tensor, add the bias, apply the function, and then the pool them all together. Alright, so we convolve our image with our weights. So you can see this is very similar to the function we had before. All the way up, a little bit higher, here. Very similar kind of idea. Get back down here. Just a little more advanced model that we're building. We still got our biases, still got our weights. We're just doing it for each one of these little 5x5 blocks that outputs 32 features. I believe that's each 5x5 contributes to 32. We'll see if there's 32 on the inside or what exactly it is. Alright, ding. Make sure to paste first. Okay. Bam, bam. What do we got? Alright, so that's the first layer that we've got going on. Of course, you got one layer. You want to clean it up. Get to this, we're sort of in the middle. We've got these features. Now we got to clean this up. We're to build a deep neural network. We stack several layers of this type. Right. So now we're going to have 64 features for each 5x5 patch. Naturally. So we make another set of weights and biases. Let's say this is layer 1. Layer 0 for computer scientists. Layer 2. And we can set up that graph a little more again. I should move this really. Right, this was us reshaping X, if you don't recall, was the pixels themselves. How dark are they? All right, what do we got here? H bool 2. Okay, second convolutional layer. Now that the image size has been reduced to 7x7, is that whatever my, hang on, 7x7 is 49, but normally it's, right, 7x7, 28 squared, 784, 784 divided by 49, 16. Not sure how I follow. I'm getting 7x7. Probably I just didn't quite follow the numbers here exactly. The 32 to the 16. All right, I will take this on faith for the moment, just to see that yes, that is what they've got. They're saying their image size has been reduced. Like it's not an image anymore. It's just a set of features, but these features still have an adjacency since it's all these 5 by 5 grids. So you can still use that information. Okay, and now we're gonna make a fully connected layer. 1024 neurons. This is pretty serious, depending how your neural. So far in this tutorial, put it that way. Or process the entire image at once. So we were doing a bunch of little small 5 by 5 things. Now everything is coming together. And the same thing before. We're going to have to reshape the tensor to be ready to do this. The 7 by 7 by 64, because we had 64 of those little guys. And then we're going to use the weight matrix and the bias again, just like before. There's our weights, there's a bias. Reshape it all into the shape again. That's this -1 to flatten. This puts it in the size that we want. And then this final line is that actual equation. Call this a big layer. Serious business, this layer. To produce overtaking, we'll apply dropout before the readout layer. I'm not familiar with dropout. This is new for me. Create a placeholder for the probability that a neuron's output is kept during dropout. Oh, so sometimes you just choose to lose the neuron's output. This allows us to turn dropout on during training and turn it off during testing. So you sort of get for your training, you get the score of it, but then you decide, it wasn't really that important. And you ditch it when you do the testing. Interesting. Automatically handles scaling neuron outputs in addition to masking them, so dropout just works without any additional scaling. Keep prob, right? The probability of keeping a particular neuron, or set of neurons, I should say. Oh, this looks like particular. HFC1 is this function. We're using the dropout here. All right, then you've got this cool neural network, but you need to actually get something out in the end. This Y-con, that's what you want. Those are the probabilities. So here we just have a final layer. They're using their simple softmax. Again, this categorical classifier at the end, because they've extracted these interesting features so far, and then you do the final computation to spit out the probabilities. So before we had a neural network that was just one computation. Here we've got a true multi-layer, deep, quote-unquote, neural network. Let's make sure we run several of these. Last thing we did was hconf1. We got a lot of things. Let's make sure we define all those. There we go. And that's the output. Okay. Well, now we have to train our actual model. To train and evaluate, we will use code that is nearly identical to the simple one-layer softmax network above. Yes. Replace the steepest gradient descent optimizer with the more sophisticated atom optimizer. Atom. We'll include the additional parameter keep prob in the feed dict, right, to determine if we want to get rid of a particular neuron, and we'll add logging every 100th iteration. And by adding logging, by adding logging, we mean that we're going to see how good it is and then spit out the results. Which that's all good. I appreciate that. It also gives you a little progress bar to let you know that yes, it's actually working. It's doing something. So again, cross entropy, that's what we optimize on. We're just using a different optimizer here than the gradient descent. Right now, you don't have to worry about what that is. I imagine this is the learning rate as before. A little bit smaller, probably because we've got a lot more variables in play. So you want to be a little careful with that. This is defining what the correct prediction is, not actually computing it as yet. Defining what the accuracy is using that vector of correct predictions. Sesh.run, we will initialize the variables, and then we'll batch 20,000. So we use more of the data here too. Train and test. Okay. also going to learn what happens when I do sesh.run and initialize variables again. I don't know, it didn't say what would happen, so let's find out. Doesn't yell at me, so that must be fine. Range 20,000. You can get through 20,000 things in Python without too much trouble. I really don't like having prints that aren't prints. Prints being functions, I feel, that is just the way it ought to be. As Python intended. Alright, so we're at step 0. We get some instant output. The accuracy is terrible. 12% it looks like. It's going through every 100, so this could take a little bit of time. Boom, that was step 100 of 20,000, so that's about 0.5% way through, I believe. My math is right. It's already up to 84%, so even just doing that, pretty good. It's going to be cranking here for a little bit. Accuracy 1. You could say, oh, we could just stop right now. Well, you really shouldn't. Don't stop. You've got the data. Oh, look, it got worse. That's funny. That's real funny. Yeah, some data is going to be cleaner than others, give you better results. So probably we thought we were better, but it actually wasn't that great. I believe this is against the actual training data here. Make sure I understand this correctly. Training accuracy, train accuracy. Yeah, this is against the data that it's given itself, so we shouldn't be surprised that it does okay in some places and terrible in others. And again, I don't have the GPU version, so this isn't going particularly fast. If you had that, this would probably go a lot quicker, just because you could subscribe a whole bunch of threads to the GPU and save yourself a lot of effort. But you can see here, generally, it takes a dive, it's going back up, pretty good. Could actually probably interrupt this at any time and say, you know what, nah, that's good enough, I'm done. And see what you got. So is there anything more to this? I think that was it. Should be approximately 99.2%. Quickly, easy build, train, evaluate a fairly sophisticated deep learning model using TensorFlow. So that's pretty cool. And this is also, so there's several more tutorials to go through. And I plan to go through several more of those in coming days, weeks, whenever I find the time. These two are clearly just to, hey, this is how you use TensorFlow if you're already used to these ideas, neural networks. If you're not, here's maybe some other things like this TensorFlow Mechanics 101. That's probably going to be interesting just to explain more of how the library works and how you're supposed to use it. This convolutional neural networks will probably be a reasonable introduction to neural nets for those of you that are sort of new to that. And they've got other things. Mandelbrot set up. I'm hoping that has some good visuals. I just want to poke at this right now. Yes, sweet. I love it. Anything that shows me graphics. I find if you can find the right way to display information, it often becomes obvious what the answer is. So I'm psyched that we're gonna get that. PDEs, I haven't done these in a long time. I'm psyched that we're gonna do some of that. Interesting. Display array, very sparse. Oh, little waveforms, cool. Sequence to sequence models I'm not familiar with. Discussed in the RNN recurrent neural networks. Cool. Get to learn some new interesting stuff. I'm just poking around at this. Print data, download. This looks like it's going to be the same kind of thing. This actually looks like it's going to go into more detail what we already did. That's okay. I'm just going to try them. See what it's like. See if it makes sense. I was trying to see if this was interactive, but it's just a picture. Although maybe it's written TensorBoard may run against a training field. Cool. Oh, fork me in GitHub. That's cool. All right, we are 10% of the way through right now. We've taken 2,000 iterations. Also note, we're getting better accuracy, but we're also using a lot more data than we were before. So I don't know if that's a true apples to apples comparison between the very simple model and this more complicated model. That would be interesting to see. I wouldn't be surprised if the very simple model essentially didn't get any better, but I would have liked to see that addressed here, saying, oh yes, we're also using a lot more data here. So that's another thing we have to account for. I mean, it was what, 1,000 data points before? What do we have? We had, yeah, we used 1,000 data points before, or 1,000 batches. Interesting. Okay, 1,000 batches of 50, and here we've got 20,000 batches of 50. So, does having 20 times more data help? This thing, maybe it would, maybe it wouldn't. You can see this bouncing back and forth. I'm actually going to kill this. I don't want to, no longer too concerned. I want to see what happens here. How good is this? Just at the end. We'll keep prob 1, so we're keeping everything. Looks like it. All the neurons. Yeah, and that's 98. Well, let's fiddle with this. Let's, you know, I don't want to keep those neurons that I'm pretty sure about. Does that make it better or worse? Playing with the data I find is important. Trying things, seeing if it works. Alright, there it got slightly worse. Alright, let's say I'm bonkers. I only want to keep those ones about that I am pretty sure about. Try it again. See what happens. Often in the process of seeing what happens, you can develop a reasonable theory behind it, and you can work through the literal math. But try things. That's the simplest thing I can suggest. Clean this up. So yeah, that was the deep MNIST for experts tutorial, because clearly having finished the for beginners, we are now an expert. So essentially we rebuilt the softmax, the multinomial categorical regression model, and then we made a true neural network. And I know I skipped through the neural network stuff kind of quick. That's okay though. This is just getting familiar with TensorFlow. Probably at some point in the future I'll do a similar kind of video walking through something that's just trying to teach you what a neural network is. And we'll see how I do with that. I have some experience, but not a lot. So that might work very well. That might work very poorly, you know. I might have a ton of tabs open here showing me how terrible I am. All right. Well, thank you very much for watching, Internet. I'm not sure when I'll be on next. I'll try to make that known. I noticed YouTube takes a long time to transcribe these videos, so hopefully that'll naturally buffer out when they're available. So, thanks for watching.